So I'm going to talk firstly about why we need quantization, particularly some of the kind of experiences I've seen talking from non-search people around some common themes. I'm going to talk about the types of quantization that we have and what we're doing. I'll also talk about better binary quantization and Elasticsearch, but I'm mainly going to focus on the Lucene capabilities under the covers. I'll mention in passing what's been added on the top, but of course I want to focus on the fundamentals of how it works. And then I'll briefly mention disk BBQ as well, which hopefully should all make sense. Right, so I've already had a nice introduction, so I don't need to do that. What is going on? Sorry, people, something else is going on. So let's check this again. Cool, there we go. Right. So if you haven't met me before, my name is Carly. So I work at Elastic. I've already been introduced, so we don't need to say anything else. We should have time for Q&A at the end. If you think of something afterwards and you want to reach out, just QR code or LinkedIn or whatever works for you is the best place to get me, basically. So we hopefully all know what vector search is. I don't need to cover this, the idea of utilizing a numerical representation to respect aspects of data that we then do vector comparisons against, and the fact that we have various different model capabilities out there for us to generate embeddings on different types of sources, be it text, images, or whatever. This isn't an introductory talk at the end of the day, so we should all hopefully know what that is. If you don't, then please shout and ask. One of the things that I'm seeing a lot is there's not a lot of thought going into actually picking out a particular embedding model. Certainly when I speak to a lot of developers, they're trying to build agentic systems, they're trying to build RAG and retrieval pipelines to go into their agents. And what I'm tending to find is they'll just pick, oh, something was the top of the MTEB leaderboard, I'm going to go with that, or I'm going to go with this model and see how it works. They're not necessarily comparing multiple, they're not evaluating, they're just trying to see, is the RAG system quick and performant? And they're not diagnosing enough into the aspects of, is it actually a relevant system? Is it returning the right results? Which is, of course, where we come in. But I saw this talk. Did anyone go to DevOps UK a few months ago, back in May? I was really slightly disappointed. The video for this talk is not up yet. Alessandra will send it round so that we can share. But there was this talk at DevOps UK. They did another version in French at Elasticon France, but it's shorter. But this talk talked really well from Benjamin and Pietro talked really well about the different ideas that they had around the fact that we get to billions of vectors in these data sets really quickly. And it's not just the fact that we have this incorrect assumption of one document is one vector and that's it. We all know that that's not the case. We know that, potentially in a document, you'll have multiple different types of embeddings. You might have a mixture of images and textual documents and data that we're doing different types of embeddings on. But one of the other things they talked about was the fact that we can get to a billion vectors very quickly. And that actually the size of the spaces that we're dealing with is actually getting astronomical. So based on their experiences of Adeline, they were talking about some of the storage requirements and the maths. Again, go check out their talk when I share it. But given if we take kind of a base case of 1,024 dimensions, we're going to end up with 4K per vector. For larger data sets, this is getting a bit scary with regards to the costs associated with the storage. Now, there is one other thing that we can do. So has anyone heard of Matryoshka embeddings? Apologies for my butchering Russian. Good. So again, not quantization, but this is basically the idea where we use Matryoshka representative learning in order to have multiple, basically, a vector comprising of multiple embedding sets within it. So it follows a three-step process. But you can see the idea here with regards to the training and the capabilities where we end up with like a really small vector, a really small embedding, which has our base representation and expands up. And obviously that is not going to impact the key performance. The gotcha that you have with some of these is that you basically need to truncate to a compatible level of dimensions. Otherwise, you're going to have an aspect of loss and performance degradation. So this is an example here of the GINA in Omni Nano version 5 model that came out back in May. And you can see here that obviously it's supporting for Matryoshka dimensions from 32 ranging all the way up to 7, 6, 8. But again, if we already have the situation of embeddings already been generated, there might be situations where we don't want to pivot to a different model and consider using these ones. We might want to consider compression as our option. And that's what quantization is compression. In really simple terms, it's compression. And this is not a new construct. So if we think about, images and me going back to like my high school computing, the idea is that we generally have two types of compression. We have lossy and lossless. Lossless obviously doesn't incur any form of loss, but lossy does. It's basically taking elements of the signals that are not necessarily, perceived as important to us as humans, and then we basically kind of shave off the edges around it. And that's what quantization is doing. We're basically shaving off aspects of it. Yes, we're losing a bit of precision with our vectors, but we should still be able to perform the necessary recall within it. So in this example, you can see with the cat, the original one, you can see very clearly that we can see the whiskers, we can see aspects of the features, but of course with lossy, we can see it's a bit more fuzzy, but the fact of the matter is we can still it's a cat. So therefore, we'll be able to still say, hey, this is a vector, this is fine. So scalar quantization is the first one. It's basically kind of like what I like to think of as the entry level to quantization. And the basic idea is that you have floating point 32 vector, and we are basically converting it to an int8 conversion. Now, in terms of how that works, basically you'll take each of the vectors that we have, and for each dimension within it, we're actually looking across the dimension values across the whole vector set, and then we're normalizing it. So you take a range of the minimum and maximum, and then we basically superimpose it into the int8 point of quantization. In terms of the storage requirements, we're going to store those actual vectors there, plus also the original max-min values, so that for each dimension you can understand how the range superimposes back. And that also gives us the advantage of being able to generate the original vector. So obviously then at query time, we're still applying the same mapping, dot product, all the rest of it, but we should be able to basically do the comparisons that we need in order to establish the similar candidates that are applicable to vector search. Now, one of the things that we need to think about with any form of lossy compression is the fact that we are introducing small errors because we are losing an aspect of the original data. So we do get some slightly different scores. Now, one of the mechanisms we can use to try and correct for some of that with any quantization method would be oversampling. And that's basically the idea of we evaluate more candidates as part of our comparisons. But when you think about it compared to the storage considerations, it normally works out as a benefit to increase the number of candidates while also taking the hit with regards to the storage. So does that make sense so far? Wonderful. Okay. So product quantization is next. So we do see this in many different kind of products available within the search ecosystem. The idea is it's a three-step process, and this is one of the things that does tend to knock people. So the first thing we have is the notion of training. So we actually take a set of our own subset of our vectors and perform a training stage against it. So what you'll see is this is the original vector at the top. There are two constants that we need to basically define. So we basically need to configure the number of what we call subspaces, which is the components we're going to split the original vector into. So here in my example, you see the M set is 4. For each of these subspace vectors, what we'll do is we are going to identify a centroid. Now, the way that we do that is we'll pull together a set of centroids. Normally, identification, it can be random, but most of the time with the solutions we're seeing, you utilize k-means clustering in order to identify centroids and then identify the closest candidate to that appropriate subvector. And then from there, that's our closest vector. So that's effectively our quantized centroid. Now, the bit that normally kind of confuses people up is that we are storing that quantized centroid, but we need to have basically a mapping table to what's called PQ codes. It's basically a glorified map like this. So you'll see this is an example code book for one of the subspaces where you have a set of keys and a corresponding value. Does that all make sense so far, is it? Awesome. Cool. Right. So obviously that's the training stage. It's, not like traditional machine learning. We don't have notions of backpropagation and really synthetic processing with regards to it, but it's a form of training nonetheless that we need to apply to our data. And that can be with regards to the upfront cost of vectors. That can be something that does put people off sometimes, particularly coming from an introductory standpoint. So the next thing we need to think about is the indexing stage. And this is obviously, again, where we do the same split, but the bit that changes is step 3, where we have the closest centroid that we're trying to find. So we actually leverage the code book that was generated and stored before in order to find the closest centroid to that particular subvector, so that then when we're actually storing the vector, we're going to store the code of the closest centroid and throw away the vector. So that's the way we get back to it, is that basically we're storing the centroid. So we are losing an element of, accuracy in with regards to our calculations when we get to query time. But at the end of the day, it's considered kind of effectively marginal when we look at the recall aspects. Then we get to the searching portion, which again is still going to use the codebook element. So you'll see that with the vector and the subvectors, we're going to find the closest centroid, again, using the PQ code lookups from the codebooks. And then we're going to calculate the dot product to get the distance between these vectors. So effectively, we're doing the multiplication element of dot product and then adding them together to get the difference. Now, part of that, I guess you also have an oversampling argument, again, to try and potentially find the edge case centroids that might not be part of particular code or residing in another code book that might not be semantically close. But you have this kind of basic idea of, this is how the kind of quantization works. Right. So now I want to talk about binary quantization. Elasticsearch, love a pun. So it's called Better Binary Quantization. They've called it BBQ. Everything has barbecue sounds everywhere. So, and it's a hot day as well. So it felt rude not to include a picture of barbecue to make people hungry. Everyone should be familiar with the Elasticsearch architecture, but for anyone who's not, who's maybe new, Elasticsearch, distributed search, and the way that it's structured is a cluster comprised of multiple nodes. Within each index, it basically matches to, it has multiple shards within it, and a shard is effectively a Apache and Lucene index, which comprises of multiple segments. So it has this notion of splitting and distributing out the problem. Now, as I said before, binary quantization, unlike product quantization, doesn't have this notion of having to train on top of a subset of your existing vectors. And that the reason for that is because it basically is maintaining a single centroid. That's how it's going to work. So yeah, that's fine. So the settings for it when we're leveraging it within Elasticsearch is that we basically specify the type option as BBQ HNSW. So it's utilizing binary quantization within HSW, which is obviously the default within Lucene and Elasticsearch. So the way that binary quantization works is we're computing a single global centroid, and we're doing that as each vector lies into Lucene segment, effectively by doing the mean of across the segment. Now, we're basically subtracting the centroid from each vector at segment flush. So that's the point where we're actually persisting the segment vectors onto disk within Lucene. We then binarize, and then we also need to store corrective scalars, which help us basically get back to the original vector again. So this is an example of what it shows the quantization. So it's really simple. It's basically if the value is greater than 0, it's going to go to 1. Otherwise, it's going to go to 0. So we'll store each respective value and we'll pack it into 8 bits. We then have to store the correction values. Now, this does get a bit interesting because partially depending on the similarity algorithm, we'll store a different number of corrective bits. So you'll see here from the note that I have in the visualization, if it's Euclidean, then we're going to store 2. For 3, it's the dot product, and cosine is actually treated as pre-normalized dot product equivalent, but you'll pre-normalize to unit length first. So actually dot product and cosine vector, aside from that minor enhancement, work in very similar ways. One of the other things that catches people out is actually binary quantization is asymmetric. And that means that we're not doing, a bit vector to a bit vector, right? We're not doing that kind of mathematical comparison. And that basically is because it would be the equivalent of calculating the Hamming distance. So in order to try and kind of reduce some of the loss and kind of improve the recall aspect, it's asymmetric. So that, as you can see from the example here, that means that we'll take the query vector and we'll actually convert that to int4 rather than to the bit vector. And then we'll do obviously bit shifting, which works equivalent way to dot product. There's a great article up there, which actually explains a lot of the maths on it. And I'm not going to. And that basically will work in an equivalent mechanism. So in terms of storage, I can't take credit for these benchmarks. I do recommend, again, reading the source up there, where Ben goes into it in a lot more detail. But you can see a comparison here of quantization comparing with the BBQ implementation. This is the Lucene number specifically for the binary quantization, along with 4, 7-bit and the raw original vector. So the main thing is we've massively reduced the memory requirements associated with the vectors. So on E5 small against 500K vectors, the memory requirement has gone from 793 meg all the way down to 57. And we've also got an impact on the indexing time, obviously, because we're storing binary. We're basically indexing and persisting binary rather than the full raw vectors. The recall versus latency was quite interesting from some of the stats that Ben did as well. So what you can see is that basically from their kind of base recall, he was finding that actually the base recall started at, 0.75. Obviously, you'd want to, for us as search researchers in this area, we'd probably be wanting to kind of boost that a little bit, but that was certainly something that was noticed as well, that, it starts off at 0.75 and it is obviously compressing up. So as the average query latency was increasing, we were also seeing an increase to the associated recall as well. Does that make sense? Cool. So there is another algorithm that has similarities to it called RabbitQ. Has anyone heard of RabbitQ or read the paper? So I have a link at the end, which has, another link to all of the resources in this talk and also to the paper as well. But you can kind of read here and you can see that some of the main differences are that single centroids used with integration with HNSW. We talked about that before with regards to the segments. BBQ doesn't have the property that the estimator is unbiased. Again, check out the paper if you want to understand more about how that works. The rescoring is not dependent on the estimated quantization error. It's only completed after initial estimated vectors. And then the other main thing is RabbitMQ, RabbitQ, the paper focused on Euclidean distance only. So obviously, binary quantization, we've talked about the correction values. It can now be applied to dot product and cosine similarity as well. And we obviously talked about the different corrective scalars that are also stored for that. So the last thing I want to talk about is disk BBQ. So this is basically a feature that Elastic have built recently and announced a few months ago. And it's basically binary quantization, but storing persistent things in disk. So you talked about before, Tamar, the idea of, the entire graph being stored in memory. Obviously, that can have a particular overhead. So there is another option known as BBQ disk. Now, to dive into the way that this works, it uses IVF, which is an acronym I absolutely hate, but it stands for inverted file index in this regard. So basically the way that IVF works is it doesn't work on the same basis of HNSW. It works based on this notion of identifying particular clusters and then having the appropriate centroid within it. So you can kind of see from the diagram that we've effectively split up our vector space into these particular centroid zones, okay? So the way that this BBQ works is it's basically storing within it the quantized vectors and the corrections and the centroids, but it's persisting them to disk. It's not holding everything within memory, which is one of the key differences that we see. There's also some other kind of things that it has on the top with regards to kind of utilizing SIMD operations, which is way low level for me, but it's actually explained in the article above if you want to check it out. Now, one of the other things that happens within it is we're utilizing a pattern known as SOAR. So this is a algorithmic enhancement that Google announced, I think earlier this year, with regards to their scan implementation. And the way that this works is that you're basically storing additional centroids. So we talked about, obviously, for that cluster visualization, that if we go back to, if you have a particular vector that's effectively on the boundary between two of these clusters, you can actually run the risk that you're not actually going to find it within the IVF implementation. So the way that we handle that instead is, obviously you could oversample multiple clusters, but the way that we do that is through here by adding in the additional PQ codes into partitions. So you're storing a bit more information, but it means that we basically managed to kind of catch that particular edge case. And again, the Google paper talks about it in a lot more detail. Right, so we talked about quantization and the types of it as an introductory level, and talked about how BBQ works in focusing on the leucine portion. There is enhancements that Elasticsearch have put on the top, again, with regards to SIMD and some quantized scalar and a couple of other things which you can read about if you're interested. And then we've talked about disk BBQ as well. Now, there's a lot of papers referenced in this article, so the QR code for the resources is the best place to go. It's basically a GitHub repo with everything in there that I've found. If you want to have a look, dive back in, have a chat with Claude about some of them and answer your questions, please feel free. And with that, if anyone has any questions, we can answer them, but thank you very much.